Welcome to the NPTEL lecture on principles and techniques of modern radar systems. In last few classes, we have seen statistical detection theory. We have applied statistical principles for the detection, because there are a lot of fluctuations present. So, today we will see some problems on that thing. The first thing is a recapitulation of your communication or in your intermediate classes in statistics. You have seen that a random variable gets completely specified by the if the probability density function can be specified. So, that is an example that x has an exponential probability distribution. Please remember, it is not Gaussian, not Rayleigh-Rice, it is an exponential probability distribution. The PDF is given by p x is equal to a to the power minus b x, x is greater than 0 and a and b are constants. Determine the relation between a and b. A and b are two constant, are there any relation? Then b is determine the mean and variance of the random variable x, then sketch p x for a is equal to 1, and finally, find the probability distribution function, which is a cumulative thing of that at any time what is the probability. This is, remember, probability density function. If you integrate that up to certain point, you get the probability distribution function. So, this is the problem, let us solve it. So, that we are calling tutorial 8 problem 1. So, how to find the relation? The first thing we know that the area under the any PDF curve should be always 1. So, we can say that minus infinity to infinity p x dx should be always 1. Now, in this case it is already said that the p x exists only for x greater than 0. So, we can say it is 0 to infinity p x dx is equal to 1, or 0 to infinity, what is the p x? A e to the power minus b x dx, that should be 1. So, you can easily do this integration, and so that will give you that a is equal to b. Okay. So, relation between a and b we are asked, that is a is equal to b. The second part, what is the mean? So, mean is, we know 0 to infinity I am writing, I am not writing minus infinity infinity. And what is it? Mean is always the first moment. So, x into a e to the power minus b x dx. So, you will have to integrate this again, the instead of e to the power minus b x, this is x e to the power minus dx. So, integration problem, if you do this integration, simple integration, it will come as 1 by a. And what is the second is what is asked? The mean and variance. So, to find variance, mean is already found, you find the second moment. Second moment is m 2, m 2 is 0 to infinity x square a e to the power minus b x dx, and again you can do it, these are all doable very easily. So, that will give you 2 by a square. So, what is variance? Remember, because in Gaussian cases generally we assume 0 mean. So, people generally say m 2 and variance same, but they are not same. Variance is m 2 minus the first moment square m 1 or mu square. Actually, I should have written this as m 1 square. So, this is 2 by a square minus 1 by a whole square. So, that gives you 1 by a square. So, this is the variance. Standard deviation is square root of that, okay, but that was not asked. So, let us not discuss that. Then part C is sketch. You see that you should be apt to sketch any given function. So, p x, what was p x? Remember, p x was a e to the power minus b x, x greater than 0. So, if I asked you to do that p x versus x, so it should start from 0, and at 0 what will be its value? That will be 1. For a is equal to 1, it is given that, otherwise it will depend on a. So, we are putting a is equal to 1. So, that is why value, otherwise it would have been a. So, 1, and then it is the e to the power minus, and a and b are same. So, e to the power minus x. So, that means the shape will be something like this. Never it will go to 0, but it is exponentially falling down, as simple as that. Then part D is the probability distribution function. So, what is probability distribution function? It is 0 to x p x dx. So, you can find out 0 to x. So, then you change this variable for a is equal to 1 e to the power minus u du. So, that if you do, it will come as 1 minus e to the power minus x. So, you can again sketch this. This is your probability distribution function. This is again x 0. So, this is the one point. Now, here at x is equal to 0, the value is 0. So, the sketch will be something like this. It is approaching this value. Okay. That is all. Then let us go to, so this is just recapitulation that you should be familiar with these things. Then let us come to our actual radar detection theory. Second problem is that the average time between false alarms is specified as 30 minutes. So, every half an hour there is a false alarm coming, and receiver bandwidth is so and so. So, what is the probability of false alarm? Okay. So, let us solve this problem. So, I can say tutorial 8 problem 2. So, part A, so I will have to find probability. We have already found out this in the theory class, that TFA into B, TFA is given, bandwidth given. So, TFA is 30 minutes, that means 30 into 60 so and so second, and bandwidth is 200 kilohertz. So, that will give you 2.78 into 10 to the power minus 9, quite good PFA. So, that operator will be able to handle it. Now, what is the question? what is the threshold to noise power ratio. That means, where you I will put the threshold. I know the noise statistics, we are assuming Gaussian noise. So, I know sigma, then how to calculate what will be the V t to achieve this PFA or TFA. So, we know that the relationship between PFA and V t that we have found out from that Rayleigh distribution and all those. So, V t square by 2 sigma square. So, PFA is known. Now, I will have to find V t square by 2 sigma square. So, V t square by 2 sigma square is nothing but minus ln PFA. So, you can put that PFA value we know. So, it will come out to be 19.70 or in dB it will be 12.95 dB. Power ratio, so 10 log, no problem. So, basically that was V t square by 2, but actually we should give what is the voltage level compared to the threshold square divided by this will be V t square by sigma square. So, that will be 3 dB more. So, it will be 15.12. So, another 3 dB more, 15.95 dB. Okay. Achha. Then part C. What is part C? Part C, repeat A and B for an average false alarm time of 1 year. Suppose we want to make false alarm time 1 year, that means each year only one will come. So, that will be very good. So, let us calculate that. So, PFA, again we will say TFA into B, and TFA will be 1 year. So, 365 days into 24 hour into 16 to 60. So, so and so second into B again 200 into 10 to the power 3. If we do that, you will get 1.59 into 10 to the power minus 13. In previous case, it was 10 to the power minus 9. Now, it is 10 to the power minus 13. Okay. So, accordingly, we can find the V t square by 2 sigma square. So, that will be 29.47, that is 14.69 dB. So, V t square by sigma square will be 3 dB more than this, that means 17.69 dB. So, if we instead of 15.95 dB, if we keep the V t square above sigma square by 17, that means 16. So, 1.7 dB only if we increase, we will get it. But remember that this will also make that various actual targets you will not be able to detect. That is why we do not do it. But if we want that we should not have false alarm, we can always do that by proper thresholding. Okay. Then next is, let us see what is part D. Assume that the threshold is to be set as in part B, that means the first case, but for some reason the threshold has been set lower by 0.3 dB. What is the resulting average time between false alarm? Good. So, by mistake or by something, suppose you have done a 0.3 dB difference. So, what is said is 20, you see Vt is voltage, threshold voltage. So, that is why I am using 20 log. So, this Vt is as in, this is the answer given in part B, minus the new Vt that I am calling, let us say Vt dashed. So, that is lower by 0.3 dB. So, that is why 0.3. So, from this I can solve for Vt, Vt dash. Vt by Vt dashed is 1.03, it will come as this if you just solve this equation. So, Vt dashed by 2 sigma square, assuming that the sigma is same in both the cases, it will come as 18.39. And so, the moment you get Vt dash by 2 sigma square, you can get PFA as 1.036 into 10 to the power minus 8. But more you see meaningful is, so PFA we got, from here we can easily find TFA. TFA will be 1 by 1.036 into 10 to the power minus 8 into bandwidth is the same 200 kilohertz. So, that will give you 8.04 minute. So, you see that instead of 30 minute, if I said the by error or something I have put the threshold just by 0.3 dB lower, but drastically the false alarm time gets reduced to 8 minute. Similarly, what is the next question is, what would be the false alarm time if the threshold is set higher by 0.3 dB. So, that is just the opposite. So, threshold TFA should increase from 30 minute in this case. So, now in this case let me call the threshold Vt double prime. So, Vt dash minus Vt 0.3, sorry 20 log that, 20 log of Vt dash, sorry 20 log Vt dash, log Vt double dashed minus 20 log Vt is 0.3. So, for that you can solve that Vt double dash by Vt will be 1.0351, and so we will get Vt double dashed square by 2 sigma square as 21.11, and that will give you a PFA of 6.8 into 10 to the power minus 10. That will give you a TFA of 2.04 hour. So, instead of 30 minute, you are getting almost 4-fold change. So, okay, that is the meaning of exponential variation. Let us see the next problem. So, this is on the Albertsheim's equation and swirling model, etc. A radar non-coherently integrates 18 pulses each of uniform amplitude, the non-fluctuating case, that means our original case or swelling 0 case. The IF bandwidth is 100 kilohertz. If the false alarm time is 20 minutes, what must be the SNR per pulse in order to achieve a probability of detection of 0.8 using Albertsheim's equation. So, so PFA false alarm time given means PFA given and probability of detection PD given. So, from Albertsheim's equation. Part B, what is the corresponding value of the SNR at the input of the envelope detector? Assume losslessism, that means now you are considering the swelling case. So, you will have to tell that. Also there is integration of pulses. So, how SNR will be there. Then part C is what would be the SNR at B above if the target cross section fluctuates according to swelling 1 model. Now, if the fluctuation is swelling 1 model, then also given fluctuation loss for PD 0.8 is 5 dB and part D is repeat part C for a target whose RCS fluctuate according to swelling 3 model. So, all the models are getting covered here. Let us solve this. This is a good problem, practical things. So, I will say that this is tutorial 3, problem number 3. So, part A is first I will have to find the false alarm time given, that means TFA given 20 minutes. So, PFA I require because Albertsheim's equation is in terms of PFA and PD. So, PFA will be 1 by 20 minutes. So, 20 into 60 into 100 kilohertz. So, that is giving 8.33 into 10 to the power minus 9 and PD is given as 0.8. So, you can find those A and B's of Albertsheim's equation ln 0.62 by 8 PFA. A depends on PFA. So, this is 18.125. Okay. Then B depends on PD ln 0.8 by 1 minus 0.8. So, that will be 1.3863. So, SNR per pulse will be Albertsheim's equation, that 18.125 plus 0.12 into 18.125 into 1.3863 plus 1.7 into 1.3863. So, that will give you SNR 23.497, which is 13.71 dB. That is all. Now, let us see part B. What is the corresponding value of the SNR at the input of the envelope detector? Assume lossless system. So, that is okay. So, lossless system, that means just 18 pulses are integrated. So, you add 18 pulses. So, it will be 18 into 23.497. So, that will be 422.95, that is 26.26 dB. Okay. Then we should see part C. Part C, I think the swirling model is getting changed. What would be the SNR at B above if the target cross section fluctuates according to swirling 1 model? Swirling 1 model given fluctuation loss is 5 dB for this PD. So, that is good. So, that means in this case we will have to add that fluctuation loss fluctuation is 5 dB. So, SNR will be 26.26 plus 5, that is 31.26 dB. And I think the next one is swirling 3 model, according to swirling 3 model. So, swirling 3 has a different LF calculation. So, LF will be based on this NE. So, that is LF whole to the power 1 by NE, and any value you can take generally 1. So, LF again comes to be 5 dB. Now, actually if you take it generally NE is varying from 1 to 2. So, you can take various values. So, if you take a thing, it will be actually it will be a bit lower, but if you take NE is equal to 1, that is a conservative estimate. So, here also SN is 31.26 dB in the safe side, but in many practical cases people take something NE is 1.2, 1.4 etc. So, in that time it will be a bit lower than this SNR will be required. That is all. You see that by this you can solve lot of practical problems by applying these swirling models and Albert-Simons equation. We have tried to show you how to do that. In assignments you will get more such questions. Thank you.